Here we go. So welcome back, everybody. This is now week 15 of class. We're really close to the end here. We're going to do one chapter on electromagnetic induction. We're going to spend a week on this, and then we'll have our third test exactly a week from today. Okay? After that, we're going to cover one more chapter before the final, which is on Maxwell's equations. We'll spend 3 days on that. So we're getting pretty close to the end of any sort of new content. Basically 5 more days in total of new content in the lecture this semester. So as usual, we have a new homework assignment. This is going to be based on the new stuff I'm presenting today. That's due next Monday. That's the day of the test. Another thing to announce is that I'm giving you a quiz on Wednesday. Now this should be the last quiz of the semester because I just don't really see us having time to fit this in any other day. So this Wednesday at the beginning of class, we'll have a quiz. It's a short quiz, about 15 minutes long as usual. And the topic is going to be how charges move in magnetic fields. Okay? So this is kind of old stuff from chapter 11, but that's the topic of the quiz. Any questions on that? Okay, and then in lab this week, we're going to be reviewing for the test. So the review packet has been out for a while. It's been available on Canvas, but we're going to spend some time in lab this week going through those problems. And just so you're aware, on Friday of this week, around noon, that's when I'm going to release the solutions. All right, so definitely need to have those to check your work and make sure you're doing things right as you're studying for the test. And of course, you should be working on your cheat sheet too. All right, there's a half sheet of paper, front and back. You can bring that into the test to sort of help you out so you don't have to remember all these equations. Okay? So I think that's it as far as introductory stuff. So let's get to the new chapter. The topic is electromagnetic induction, and this is coming from chapter 13 of volume 2 of our OpenStax textbook. All right, so let's do an introduction first. I'm going to tell you what electromagnetic induction means, but to even really get there or to start describing it mathematically, I need to define a new quantity called magnetic flux, okay? So we've heard of this term flux before, right? What was the context for that? We didn't learn about magnetic flux, we learned about electric flux, right? Back in the Gauss's law lecture. So this is going to be a very similar idea as far as flux is concerned, but how it's applied in our equation is very different, okay? So we'll get to all that. First, a little bit of history. The stuff that we're going to learn about was basically independently discovered by these two guys who lived in the late 1700s to the mid 1800s and did most of their work in the early to mid 1800s. So this is some pretty old physics still, but we're getting closer to the modern era. And you know, to understand what electromagnetic induction is, let's take a step back and think about some things we've learned about magnetism so far, okay? So the first thing we learned is that if you have a charge in a magnetic field, okay, this could be like a single proton or a single electron, some kind of charged particle moving through a magnetic field, we know that magnetic field can exert a force on the particle. And that's not only true for just individual particles, it's also true for tons of particles moving together, i.e. an electric current in a wire. That will also feel a force from a magnetic field. All right, so that was all chapter 11 stuff. Then, in the most recent chapter, chapter 12, we learned that, well, where do magnetic fields come from in the first place? They result from the fact that charges are moving. So if you have a wire that carries a current, it's going to produce a magnetic field all around it, and actually, same for individual moving charges. Okay, so that's what we know about magnetic fields so far, but here's what we're going to learn about next. Because electromagnetic induction is basically a process where you have a changing magnetic field. Okay, the magnetic field is not something that's just staying the same over time, it's not constant, it's now a changing quantity. And if we have a changing magnetic field, what it does is it creates an EMF. We learned about this idea of EMF before. It's basically another way of saying, for our purposes, producing a voltage, okay? So you have a changing magnetic field, it produces a voltage, or an EMF, which can then cause current to start flowing. Okay, that's really a summary of this idea of electromagnetic induction. And again, this was independently discovered in a laboratory by these two guys. Michael Faraday, he gets kind of the credit because the law is named after him, as it turns out. So we'll learn about Faraday's law, but Joseph Henry also deserves some credit. So they both kind of discovered this phenomenon. All right. So let me tell you about some of these experiments, particularly Faraday's experiments that led us to discover this idea of electromagnetic induction. And then I'm going to show you sort of a tabletop version of one of those experiments. Okay? So here's the setup, everybody. We have a battery, okay? And that battery is connected to a wire. And then if we follow that wire from the battery, you see it's wrapped several times around this iron toroid. So this is just a piece of iron that's kind of in a donut shape, okay? And then we have a switch. So that circuit is not complete because the switch for the time being is currently open. But of course, if we close the switch, we can complete the circuit and then some current can start to flow, all right? Now, that's not all that's going on. On the other side of this iron toroid, we have another piece of wire wrapped around many, many times. What is this hooked up to? It's hooked up to something called a galvanometer, which is just something that measures current, okay? It's an old school term for an ammeter, something that can detect current, all right? So we can kind of think of this as being two separate circuits. Circuit number one connected to the battery, and then circuit number two connected to the galvanometer. And what we want to do is think about what happens when we close the switch, all right? So this is what Faraday observed. He had a circuit that looked very similar to this one. And what he did is he went ahead and closed that switch. And he wasn't really even expecting to see this, but what he saw to his surprise is when this switch was initially closed, this needle over here briefly deflected, which means for a short time, there was actually some current in this second circuit, okay? Now that's surprising because that circuit doesn't have a battery or anything that we would normally expect to be driving a current. And also, the current was very short-lived, right? So it just kind of briefly deflected, indicating there was some current there for a brief time, and then pretty much went right back to zero. Another surprising thing is, okay, we have the switch closed for a long time. There's current that's just constantly flowing through this part. We open up the switch again, okay? What happens in that case? Well, this needle, again, briefly deflects, but actually in the other direction, okay? So there's a lot to say about this, but here's what Faraday was able to kind of conclude, determine what was going on. He concluded that it's the fact that you have a changing magnetic field in this toroid that is inducing a current to start flowing in this part of the circuit. Now let's try to understand that for a second, right? When the switch is first closed, you're going from no current in this circuit at all, right? And then after a short time, you reach some sort of steady current in that circuit. So there's a brief period of time where the amount of current in this circuit is ramping up, right? Okay, well, if the current is ramping up, that means the magnetic field that's created by that current is also ramping up, okay? So there's a changing magnetic field. When there's that changing magnetic field, that's when we saw this deflection over here, right? That's when we saw current being created over here. And then same thing when you open the switch again, right? You start with a steady current, and then that current pretty quickly goes to zero. So you have a changing magnetic field for that short time. And again, that's when we produce current over here. So to summarize, this is what Faraday found. If you have a changing magnetic field, you can induce some current to start flowing here, where you would normally not expect any current, because again, there's no battery or generator or anything else that we normally associate with driving a current, okay? So are we all clear on what this experiment says? Now here's a much simpler type of experiment. So if it's really true that all you need is sort of like a changing magnetic field of some kind, and then that can induce a current to flow, why don't you just do this? Why don't you just take a magnet and then take a little loop of wire, connect it to, let's say, a light bulb, okay? And again, in that loop, you have no battery, just a loop of wire connected to a light bulb. So take that magnet and move it through the loop. So basically, the magnetic field that the loop sees is changing, right? It sees a pretty weak field at first, but then as the magnet goes through it, it sees a stronger field, more field lines going through it. And while that change is happening, we can have some current flow through here, which will cause the light bulb to light up, okay? So that's just another example of the same effect. You see how these two experiments are related? By the way, you know, this is the operating principle behind electrical generators. Pretty much all of the power in our electrical grid in the modern era is coming from generators which operate based on this basic idea, okay? So let me show you in real life an example of this. So here is my coil, right? And all I'm doing is I'm hooking this up to a voltmeter, and I have a strong magnet here. You guys can watch. All I'm going to do is move that magnet through and then back out real quick. Okay, so you see, for that brief period of time where there was a changing magnetic field within this coil, that's when some current was induced to start flowing in that coil. Okay? By the way, it's really important that's a changing magnetic field, because what happens if I just put the magnet in there and don't move it at all? What's going on?
Feels like zero.
Yeah, there's no current induced in that case. So it's really the fact that the magnetic field is changing, that's what's inducing the current, okay? And that's what's different about this chapter from the previous ones. Previous chapters, we've dealt with static situations where you just have a constant magnetic field. This is something fundamentally different about changing magnetic fields, okay? All right, so now, hopefully you see what the basic effect that we're learning about is. Now we want to be able to develop some equations to describe it a little more precisely. So in order to do that, we're going to need to define this quantity here called magnetic flux. Okay, magnetic flux is part of the equations that we'll start developing. And this should all look very familiar, okay, because we did in the second chapter on Gauss's law, electric flux. So magnetic flux is a way of quantifying how many B field lines are going through a surface, okay? So flux is relative to some surface that you define. If I have a lot of B field lines going through that surface, then I have a large amount of flux, okay? If I have no B field lines going through a surface, then I have zero flux. That's the basic idea. And the definition is pretty much the same as with electric flux. So we use capital phi to denote flux. For electric flux, we'll put the subscript E. For magnetic flux, we'll put the subscript B. So remember how this worked for electric flux. The electric flux through a surface was given by integral E dot dA. Okay? It's given by the integral of E dot dA. And when it comes to magnetic flux, it's the same basic idea, except we do the integral over the surface of B dot dA. Okay? So let me just remind you how this works. We have our B field, that's shown with the red lines here, and then we have our surface, that's shown in green here. So B is obviously the magnetic field vector. dA, that's what we call an area vector, okay? So it's a vector that goes perpendicular to our surface, that's how its direction is defined, and it's a little infinitesimal piece of the overall area of the surface, okay? So when you do B dot dA, that applies to just that infinitesimal element. We have to integrate over all of those infinitesimal areas to get the full flux, okay? So, all looking familiar, hopefully? We've done this before, just now with magnetic fields. All right, so let me ask you this. Let's say we have this kind of situation where we have a flat surface with dimensions 35 centimeters long and 75 centimeters high. Okay? there is a B field with a magnitude of 1.75 Tesla going through this surface. And let's say the B field is uniform. So it just has a value of 1.75 Tesla everywhere. That's not changing from place to place, right? So one thing that we can mess around with is the angle that the B field lines go through the surface. I'm calling that theta here. So I'm going to ask you two questions. First, calculate the magnetic flux through the surface when this angle is 30 degrees. And then along with that, see what units pop out. Okay, there's going to be a natural unit that pops out when you calculate this flux. And then do the same exact thing when the angle is 90 degrees. Okay, see what you get. So take about, I don't know, 2-3 minutes to go through that, and then we'll discuss it together. So the nice thing about this one is the B field is uniform, so you can just pull that out of the integral pretty much right away. Okay, so I can see some people are already starting to get this. Let's give you another minute or so. We're still working. Okay, how about we go through this? So, first thing I want to show you is that the expression we have for magnetic flux can be simplified a lot, okay? So in general, it's given by the integral B dot dA over some surface, right? But we know that a dot product is given by B times dA times cosine of the angle between these two vectors, okay? And here's what we can do next, specifically in this case. So B, the magnitude of it, that's the same all over the surface. So that's going to be something we can pull out. And also the angle, right? The angle is the same everywhere along the surface because the surface is perfectly flat, it doesn't curve. So basically, because we have a uniform B field and a flat surface, both of those are things that get pulled out of the integral, and then all we're left with is integral dA. But here's the thing, I mean, integral dA is just adding up all the little bits of area on our surface. So of course, once we do that, we just get the total area, which I'll call capital A. So this is B, A, cos phi, okay? Can anyone think of sort of a different way to write that? I could just write it as B dotted with A. So the B field dotted with the full area vector of the surface. Okay. So if it's non-uniform B field, we have to actually go through the work of doing that integral. In this case, we can use this result. All right? And that should be familiar from the electric fields stuff that we did previously. Okay? So with that said, let's do the two different calculations. When the angle is 30 degrees, here's what we have. The magnetic flux, phi b, is equal to, I'm going to take the strength of our B field, which was 1.75 Tesla. Then I'll multiply by the area. It's just a simple rectangle, so just do width times height. 0.350 centimeters times 0.750 meters. Sorry, that should say 0.350 meters times 0.75 meters. And then we have cosine 30. What do we get numerically for this?
0.398.
So yeah, you should get 0.398. And what units do we end up with?
That's 1 meter squared.
Yeah, so it's basically going to be the magnetic field unit of Tesla times the area unit of meters squared. Okay? Now, can anyone tell me what happens when I make the angle 90 degrees? Yeah, this should immediately be 0. I'm not even going to write the numbers. I'm just going to say B times A cosine 90. Regardless of what the B field strength and what the area actually are, this cosine 90 factor is always going to give us 0, right? So what that means is, if you have an angle of 90 degrees, that's kind of a special case where the flux goes to 0. Try to envision this, right? Let's say this is our flat rectangular surface, this sheet of paper. The area vector is perpendicular to the sheet, so if I'm holding it this way, let's say that's going straight up, okay? Now, if I'm imagining the B field is perpendicular to this area vector, that means it's kind of just going across the sheet like this, right? In other words, lines of the B field are not going through the sheet at all in this orientation. Make sense? So that's why we say there's no flux. All right, so we good on that? So that's one example of calculating magnetic flux. Let me show you another example. Now in the example I just gave you, again, we were pretty much able to get around doing any sort of integration because it was a uniform B field and the surface was perfectly flat. In this case, we're not going to be able to do that. We're going to be forced to do the integral because the B field is non-uniform. Okay, so here's what's going on. We have a long straight wire that carries a direct current I. So here's the wire carrying current I on the left side of the figure. All right, there's a rectangular loop of wire with dimensions L by W. So this is the length here, this is the width here, and the distance of that loop from the wire carrying the current is D. Okay, so we have a straight wire, there's some current going through it, and then some distance away from that, we have this rectangular loop of wire with dimensions L by W. That's what's going on. Okay. So the question is, what is the total magnetic flux through this loop? We're going to just calculate it using the integral B dot dA, but I'm going to tell you right away, we can't get around integrating because B is not uniform. Let me remind you how this works. If we have a wire that carries a current, it's just a straight, infinitely long wire. The B field is given by this expression here, mu naught times I divided by 2 pi r. We recall this? How about the direction? So it's the right-hand rule. Point your thumb up, going with the current. We know that the B field lines loop around the wire. So on this side, at least, they're all going into the page. So where this loop right here is located, I have a bunch of B field vectors going in, all right? But the thing is, the B field is strongest right next to the wire, and then it gets weaker as you go out. So that's what I mean by it's not uniform. It's not the same strength everywhere. So here's how we're going to deal with this one. So we have to kind of find some way of setting up the integral, right? So let's start just by copying down the picture. We have the straight wire with current I going through it. And then we have our loop over here. Now the thing about the B field is it depends on how far we are from the wire. So I'm going to break this loop into little strips like this. So I'm just going to select some random strip of the wire. I'll shade it so we know which one I'm talking about. And let's say that that strip is located a distance r away. And then let's say that has a certain thickness to it, which I'll call dr. And of course, this right here is the length of that strip, which we're calling L. Okay? So I already established that we have a B field, which is pointing in into the page. And our area vector, by the way, remember that's got to be perpendicular to this rectangular loop. It turns out it's a little ambiguous. I could say it's coming out of the page like this or going into the page like that. It doesn't really matter for our purposes. So I'm just going to define the area vector as going into the page. Again, as long as it's perpendicular to our loop, it works. So that kind of sets things up for us where we can do this integral. So here's what we have. We have the magnetic flux, which again characterizes how magnetic field lines are going through this surface. It's given by the integral B dot dA. Okay? So let's break that down a little bit. This can be written as the magnitude of the B field times the magnitude of the area vector dA times cosine of some angle. But hopefully you can see that both of these are just going into the page, so that there's 0 degrees between them, okay? Okay, now, at this step, I can't pull out B because it's not the same strength all over the loop. So I have to figure out a way to set this integral up. So here's what we can do. The strength of the B field is given by u0 times I divided by 2 pi r, right? It just depends on how far away we are from the wire. And then dA is how much area is in this infinitesimal little strip. Can someone tell me what that dA should be? Like, what's the area? What is it? It's L times dr, right? It's a rectangular area. It's the length times the thickness dr. And I should put some limits on that. Maybe I'll do that on the next line. But of course, the limits will allow us to cover the entire rectangular loop and not just some small piece of it, right? But in order to do that, I'm just going to note a few other distances on this diagram. Remember, D, that's how far away this edge of our loop is from the wire. And then W is how wide it is going this way. Okay, so check this out. We have an integral. We're integrating over R, right? Because we want to go starting here at this edge on the left, all the way out to this edge on the right. But we can pull out anything that does not have an R in it, because those are constants. So we have u0 times I times L divided by 2 pi. That's the full set of constants we can just remove from the integral. And then what do we have? We have dr divided by r. Now, let's put limits on that. What should my limits of integration be? So in terms of the smallest r value to the largest. Yeah, so r, when we're at the very left edge, starts at d, that's just however far away we are. And then d plus w to get to this edge. Okay, so those are the limits. This goes from D to D plus W. Now, what does 1 over R work out to when we integrate it?
Natural.
That gives you natural log, if you recall. So what we have is mu naught times I times L divided by 2 pi. This works out to natural log R, and we take that from D all the way out to D plus W. Okay, so just to do a little more work, we have mu naught times I times L divided by 2 pi. And then let's plug in the top limit. I have natural log D plus W minus, plug in the bottom limit, natural log D. What can I do to combine those two natural log terms? Yeah, they can be divided within the same natural log because that's the subtraction property. So I have natural log D plus W on top divided by D on the bottom. I could do that. And then maybe just to simplify it one step further, I'll write this as mu naught times I times L divided by 2 pi times the natural log. Okay, if I have D over D, that's just 1. And then the other term is plus W over D. So that's just how I'm going to write it. Okay? So that's a symbolic formula for the total flux through this surface, given that this is a non-uniform field. Okay? So any questions on how I sort of set this all up for the integral? All right, so I think that's enough examples of just calculating flux. Now let's try to take that next step. How can we incorporate this idea into some kind of equation to describe induction, this effect that we just talked about? So here's the result. We have, again, mu naught times I times L over 2 pi, natural log 1 plus W over D. That's where it came from. Okay. So here's the next step, everybody. I'm going to tell you about actually 2 different laws. They're related to each other. They're both describing this effect of electromagnetic induction, but they're kind of 2 aspects of it that we need to get right, okay? So let's start with Faraday's law. Here's the idea behind Faraday's law, which I've already described, but I'll say it again. Okay, if we have a changing magnetic flux, specifically, let's think about through a coil of wire, right? I showed you the example with this coil of wire and a few others on the slides. Let's say we have a magnetic flux through a coil of wire which is changing, okay? That induces an EMF in that coil. And that EMF in the coil kind of acts like a battery, which drives current around, okay? The other thing to note is that sometimes if we have a coil of wire, we're not just going to sort of loop it around one time, right? Oftentimes we wrap several turns of wire around the same coil. It turns out if there are n turns of wire, the same EMF gets induced in each one. So there's sort of like a multiplicative thing going on where, you know, if I have 10 turns of wire, I get 10 times the EMF induced as if I just had 1 turn, okay? So the total EMF induced in a coil is given by this. This is Faraday's law, probably in like the simplest form you could write it. There's different ways you can write it, but this is the most compact way to do it. This says the magnitude of the EMF, so we're not really worrying about the sign, we're taking the absolute value here, just keep that in mind, is equal to N. Remember, that's how many turns of wire are in the coil times what? The derivative of our magnetic flux with respect to time. This is the time rate of change of our magnetic flux, okay? Again, give that by psi b. And I put absolute values around here because, again, this is just giving us a magnitude, not any thought about the sign yet. It's Lenz's law, actually, that tells us what the correct sign should be. Okay, so how should we think about the direction of the induced EMF? Okay, this gets a little tricky. So we're going to do a lot of examples of it, but let's just try to see what the statement is. Lenz's law says that the induced EMF causes current in this coil to flow in a direction that opposes the change in magnetic flux. All right? So let's take a look at this example as a way of understanding Lenz's law, okay? So what's going on in this picture? We have a single loop of wire like this. That's our coil, right? And then we have just a magnet which we're just going to push into that coil. Let's say with the north pole of the magnet facing forward. So we know what the magnetic field looks like, right? The lines are kind of coming out of the north pole like this. So would you agree that as we get closer and closer, that there are just more field lines going through this coil? In other words, the flux of lines going to the right through this coil is increasing, right? As we move the magnet, there's more and more lines going through the coil to the right. So what does it mean to oppose the change in flux? It means we're going to have some field lines going to the left being created here, okay? How can we do that? By having current induced going this way around the coil. Let's think about that with the right-hand rule, okay? Remember, one way to do the right-hand rule is to take your thumb and put it in the direction of the current. So my field lines that get created by current running through the coil this way, not the field lines from the magnet, but from current running through this coil, those would tend to go this way, right? That's opposing the change in flux that's happening by pushing the magnet that way. So when we induce this current to start flowing, it's opposing the change in flux that's creating the current in the first place, okay? That's how Lenz's law works. So you don't try to amplify the change, you try to oppose the change. That's just the way our universe happens to work, okay? I don't know why that is, but that's the way our universe works, okay? So is that clear enough? We're going to do some examples, but again, we induce current to oppose the change in flux. That's the takeaway. Go ahead.
Is there a mathematical explanation for any of this? Or is
Well,
it
I mean,
like, oh, okay.
Okay, you can, yeah. Well, I'm going to show you in a second an equation that kind of encapsulates it a little more compactly, right? But yeah, then you could ask, well, why is there a negative sign in that equation? It's just like, at some level, it's just, well, that's just the equation that works. Yeah.
Sounds good.
You can, yeah, you dig deep enough, you just hit rock bottom at some point. Okay, so yeah, I will say that generally, we're not going to be using this form of it. We're going to be using the form of Faraday's law that I showed you on the previous slide most often. But I want to show you this form of it, which kind of, I don't know, is a little more clean or encapsulates everything all at once a little better. And it's also more general, okay? Because all of the examples of induction that I've showed you so far involve some kind of coil of wire and changing the magnetic flux through that coil to induce some current to start flowing in that coil, right? In general, you don't even, you don't need a coil of wire. There's nothing special about having a coil of wire present, right? This is a more general phenomenon. So in general, here's what Faraday's law really says. If you have a changing magnetic field, just like anywhere in space, okay? It can be somewhere like this, where there's a coil of wire present, and I can see the effect of that, or it could just be perfectly empty space. It doesn't really matter, actually, okay? What that does is it produces an electric field, okay? Really what's going on is you're creating an electric field. And that electric field is what is pushing current around and creating this current that we saw flowing in our demo, right? So that electric field is going to be there even if you don't have a circuit for it to push charges around within, okay? So the more general way to see this is the following. So we have d dt, that's the time derivative on this side, of b dot dA. That's the time derivative of the magnetic flux. That's the same as before, right? That there's a changing magnetic flux. So we take the time derivative of it to say there's some change going on. On this side, what do we have? We have E dot dL. And hopefully you remember that E dot dL is the same as voltage or EMF, right? So if we're creating some kind of voltage that's causing current to start flowing in a loop, there's an E field ultimately underlying that, and E dot dl is the voltage. That's the definition of voltage, okay? So here's the picture you should have, right? Let's say I've got B field lines going this way, all right? And this is kind of like an imaginary surface that we just sort of put there to analyze what's going on, okay? Now clearly, if the strength of this B field is changing in some way, right, then the flux through this little surface that I drew is going to be changing, right? If it's getting stronger over time, then I'll have more flux over time, or if it's getting weaker, I'll have less flux as time goes on. What this equation is telling us is, as long as I have a changing flux through that surface, I'm going to have an E field that kind of loops around the surface like this, such that there's an E dot dl that's non-zero when I go around the loop. All right? There's a negative sign there, by the way. That negative sign tells us that the induced EMF opposes the change in flux. Okay? So that's Lenz's law, that the induced EMF opposes the change in flux. Again, this is probably not what we're going to use most of the time to solve problems, but just wanted to show you that there's a sort of more general way to think about this. Okay, so how about we move on to something practical. How do we apply Faraday's law and Lenz's law? Okay, we do lots of examples. Let's start by talking about Faraday's law, okay? Now, most of the time, we're going to use Faraday's law to try to predict how much current is going to start flowing in some kind of coil, given the fact that there's a changing magnetic flux through that coil, okay? So Faraday's law is basically going to be used to find the magnitude of that induced EMF in the coil. And if we know the induced EMF in the coil, we can get the induced current, because the EMF, i.e. the voltage, and the current, I, are related by Ohm's law, okay? So oftentimes we take two steps like this. We use Faraday's law, which says the magnitude of that induced EMF is given by N, that's how many turns of wire in our coil, times the derivative of our magnetic flux through that coil. So the time derivative of the magnetic flux. And again, we use absolute values because this is not what we use typically to find the sign. Now, Ohm's law says that same EMF is the current that's going to be induced in the coil times the resistance. Okay, this is just V equals IR, but we're just using a different symbol for the voltage. Okay? So, let's talk about three cases we're going to see here. Basically, there are three different ways magnetic flux can be changing. Okay? Because what does flux depend on? It depends on how strong the B field is. It depends on the area as well. But it also depends on the angle between your B field and your area vector. And if we need flux to be changing, that means one of those three things is going to be changing, right? So either the area of our coil changes, the strength of the magnetic field that's going through the coil, that's changing, or the orientation is changing. Like the angle between the coil and the B field is changing. Any one of these will give you a changing magnetic flux and will induce an EMF in the coil. So I'm going to show you examples of each type of these problems. Okay? Any questions? All right. So how about using Lenz's law? Again, Faraday's law says we get an induced EMF, which may cause some current to start running through a coil. Lenz's law tells us what direction does current start flowing in the coil. So remember this, the induced current in the coil is going to oppose the change in magnetic flux going through that coil. Now that kind of makes sense, but how do we break that down into some steps we can follow so I just get the right answer every time? So try this, okay? If you follow these steps, you'll never get the direction wrong. So here, step one. Determine whether the magnetic flux through your coil is increasing or decreasing. That's pretty straightforward, right? Like if I have more field lines going through the coil over time, I have an increasing flux. If I have less field lines going through the coil over time, then I have a decreasing flux. So one of those things is going to be happening. Just try to figure out which one. All right, once you've determined that, if we've determined that our flux is increasing, that means some current in our coil is going to be induced. That's going in the opposite direction as our external B field. Okay, so think about this, right? We have some B field that is just going through our coil, right? Then we call that B external. That's what we're going to call it. We also have what I'm going to call B induced. That comes from the fact that current starts going through your coil, that creates its own B field, right? So these two different B fields you want to kind of think about here, okay? If we're increasing in flux, the induced B field is going to have to oppose the external B field, okay? Because that's going to oppose the change, okay? On the other hand, if we're decreasing in flux, then the B field that gets induced is actually in the same direction. Because think about it, right? If I have an external B field going through this surface, and let's say that B field is getting weaker over time, right? So less field lines are going this way through the surface. Lenz's law works out so that we get more field lines going through that surface as a result of inducing this current, right? That's how we oppose the change. We want to keep things how they were, right? Okay, so lastly, once we know the direction of the induced B field, it really just depends on which of these two cases we're dealing with. The right-hand rule gives you the direction of the current, okay? I know that's a lot to take in, so we're going to do like 3 examples of this, and hopefully after the examples, it makes sense if this all just like seems like gibberish, okay? So, any clarifications? Are you ready to see the examples? Okay, let's go to these examples. So, I'm going to start with one that we just go through all together, okay? And then I'll have a couple that you can try out, okay? So here's the scenario. We have a circular loop of wire that's being pushed into a magnetic field. So we imagine that there's a magnetic field where the field lines are going into the page. But the field really only exists within this little box. It's essentially just 0 outside of that box, okay? So the question is, what would the induced current in the loop be? So I hope you can see that this is an example where induction would be going on, because as we push this loop into our B field, the flux through that loop is changing, right? There's more field lines going through the loop as time goes on, as we're pushing it into this field. So because we have a changing flux through the loop, we're going to induce some current to start flowing in that loop, as long as that change is happening. And it can really just be either clockwise or counterclockwise from our perspective, right? We have to figure out which one it is. All right, so let's follow those steps that I told you about before, right? First, is the flux through this loop increasing or decreasing? Well, in this case, it's clearly increasing. Right before we even enter the field, we have 0 flux. And then as we have this left edge, like barely enter the field, we have a small amount of flux. And then that just grows as we push it further and further, because more and more lines will be going through. So it's an increasing flux due to the external B field. And by the way, this is our external B field, right? Cool. So that makes sense? So now, because we know the flux is increasing, we can take the next step, which is, all right, the B field that gets induced by current flowing through this coil, which way does that have to go? Well, because again, flux is increasing, the B induced must be opposite to the B external to oppose the change in flux, right? Because the idea is, if we have more and more field lines going through this loop that are going into the page, to oppose that change, we want to create some field lines coming in the opposite direction, out of the page, right? So the induced B field is out of the page. So, we good on that so far? So now you guys tell me, how would current have to flow within this coil so that it creates a B field that's coming out of the page. Yeah, so we can try it both ways, right? So take your thumb. Let's suppose we're going counterclockwise like this, right? So I take my thumb and kind of point it that way. And so yeah, I'd have some B field lines coming out of the page in that case. If my current were going the other way, my B field would be going in the wrong direction, right? So it looks like, yeah, the induced current is counterclockwise to oppose the change in flux. All right, make sense? All right, let's see if it makes sense. Let's have you try one out. Actually, any questions on this one before I give you another example? All right, so try this one, okay? So you have a circular loop of wire, which is initially in this B field, which points out of the page. And what we do is we take that loop, which is completely immersed in the B field at first, and then, again, remove it from the B field. So while we're pulling it out of the B field, which way do we have current flowing within the loop? So think it over. You might be able to kind of see it right away, but try following those steps, okay? Yeah. Flux is decreasing. We just carry, yeah, all that matters is we're in the process of taking it out of the field. Yeah. All right, let's put this one to a vote. I think some of you have the answer, but I just want to see what you think, you guys. So, votes for clockwise, counterclockwise. You got it. Cool. Again, just in case, I want to take you through the steps because some of these examples are easier than others. Some you might just be able to kind of see. For the ones that don't immediately, make themselves obvious, you want to kind of follow the steps. So, first of all, this is our external B field. It's coming out of the page. And because we're moving the loop out of that B field, the flux is decreasing, right? So what I'm going to write is flux, this is magnetic flux, side B, is decreasing. Okay, now because it's decreasing, we immediately know what to do next. The induced B field has to go in the same direction as our external B field. So B induced, let's say, goes with B external, right? Because if our flux is decreasing and we're trying to oppose the change in flux, well, we need more B field lines coming out of the page to oppose the change that's happening, right? So that means B induced is out of the page, correct? And what kind of current is going to create a B field going through this coil that's coming out of the page? Well, once again, it's going to be a counterclockwise induced current. So like this. And again, verify this with the right-hand rule. If you put your thumb going that way, you'll see that your B field lines in the middle of the loop are coming out of the page, which is what needs to happen. Okay? Any questions on that? Okay. Let's do some more. So here's the scenario. We have a circular loop of wire, and it's inside of this uniform magnetic field, which points into the page. So, by the way, just a point of clarification, when we say uniform, we mean it's the same everywhere in space, right? That's not the same as constant. Constant means it doesn't change over time, okay? So uniform is about staying the same all throughout space. Constant is about staying the same over time, okay? So we have a uniform B field, but it's changing over time. So it's got the same value everywhere, but it's just getting weaker over time. Does that make sense? So if the strength of our magnetic field is decreasing over time, what's our induced current? Clockwise or counterclockwise? And then as a follow-up to that, what's the direction of the E field? Because as we know, if we induce some current, there must be an E field kind of pushing everything around, right? So try to answer both of those questions, then we'll go through it together. Should take maybe a minute or two on this one.
The word referring to the induced current, is that conventional current?
Yep, yeah, good question. This is conventional current. Yeah, we always assume conventional current. Okay, let's take a vote. First question, what is the direction of the induced current? Who says we have a clockwise current? Counterclockwise? Okay, good. What about the E field? Clockwise? Counterclockwise? Okay, so for that second one, it's the same answer, clockwise. Remember, the E field that exists in a wire that has current flowing through it just points in the same exact direction as the conventional current. You can think of it as what's causing charges to be pushed around within that wire, okay? So it goes with the conventional current. Does that make sense? All right, so again, this might be overkill, but I want to go through the steps. So we have an external field, which is going into the page, and the strength of that field is decreasing, right? So if the strength of the field is decreasing, then our magnetic flux through the coil is also decreasing, right? So that's step one. Now, when we have a situation where flux is decreasing, the induced field, does it go with or against the external field? Yeah, it has to go in the same direction. Let's say it goes in the same direction as the external in order to oppose the change in flux. That's what has to happen. So that means your B induced is into the page. Okay? To create a B field going through the loop that's going into the page, it actually requires this type of current by the right-hand rule. Remember, point your thumb whichever way you think the current's going, and your fingers will curl in the direction that your induced B field is going. Okay? So we must be going clockwise like this. Induced current, clockwise. Okay? And then lastly, your E field goes with the conventional current direction when you have current flowing in a circuit. So therefore, that is also clockwise. All right? So that's how we sort of reason this all out. All right, so any questions? Think we got it? So far, all the examples you've seen are Lenz's laws examples, right? So I'm going to show you some examples now of Faraday's law. So not only do we want to say that in this situation, we get some current induced, which is going clockwise or counterclockwise or whatever, we want to say how much current. We want to quantify these things. And that's where Faraday's law is going to come in, okay? So here's what's going on with this one. In this example, we have a square loop of wire with a side length L equal to 19.5 centimeters. This square loop lies in the plane of the page. The loop is inside of a uniform magnetic field, which is going out of the page like this. So there's your external B field coming out of the page. Now, if this B field doesn't change in any way, doesn't change its strength in any way, nothing is going to happen. You're not going to induce any current. It's only when the B field strength is changing that you end up inducing some current in this loop. Okay, so let's say that the strength of the magnetic field is increasing over time, and it's doing so according to this function. Okay, so what is this function telling us? It's telling us that B, as a function of time, is 0.45 t squared, t is time, times 0.9 t plus 1. Okay, so try this out. Plug in, let's say t equals 0. We get 0 here, 0 here. That means we start off at a strength of 1 Tesla. But as you put in higher values of t, you'll see you get larger values of the B field coming out. So this is a function describing a B field which is increasing in its strength over time. Okay? So here's what we're going to do. Let's say this loop consists of just one single turn of wire. And the resistance in that single turn of wire is 0.15 ohms. So 2 questions. What is the current induced at t equals 1 second? And then what is the current induced at t equals 3 seconds? In other words, how many amps of current are going to be circulating in this loop at those 2 different times? Okay? So that's great. We can definitely figure out what that current is. But can someone tell me which way it's going to go, clockwise or counterclockwise? All right. Who thinks it's going to go clockwise? Who thinks it's going to go counterclockwise? It is going clockwise, okay? So I'm not even going to write anything down for this one. Let's just reason it out, okay? We have an external B field, which is coming out of the page like this, correct? And the strength of that B field is growing over time. That means the flux through our loop is growing over time. It's increasing, correct? That means we need to induce some kind of B field going in the opposite direction in order to oppose that change, right? So we want an induced B field going into the page, right? Induced B field going into the page is only possible with a clockwise current, okay? So we induce a clockwise current. Does that make sense? Okay. All right, great. So we know it's clockwise. Now let's calculate amps, okay? So let's first do this. let's come up with some way of writing the flux through the loop. What was that? Okay. Let's come up with some way of writing the magnetic flux through the loop. So this is given by phi b, right? Which is b dot dA integrated over the entire loop. Now in this case, we do have a uniform B field. Doesn't vary from place to place. And also, our surface is perfectly flat, right? So we don't really need to do this integral. We can just do b dot A. And again, the reason is we have a uniform field and a flat surface that the field is going through. So whenever that's the case, we can just get around doing the integral. Okay, also remember this, that b dot A is just magnitude B, magnitude A, cosine of the angle between them. Now let me ask you, in this case, what goes in for that angle right there? What are we thinking? It should be 0 degrees, right? Because if this is our area, just a square, right? The area vector is going to be perpendicular to that, so coming out of the page basically, which is the same as our B field, right? Coming out of the page. So A and B are both just coming out like this, so there's no angle between them. All right? The last thing we can do is say, well, B is what it is. We'll put in the function in a second, but the area of a square is given by what? What's the formula for the area of a square? It's just the side length L squared, right? So that's what we've got. That's the flux through the loop. So now, the induced EMF in the loop. So in other words, it's kind of like if we just had a battery with a certain voltage that we stuck in the loop, what would the effect of that be? You can really think of it in those terms. Well, that's given by Faraday's law, which says the magnitude of that induced EMF is equal to N, that's the number of turns in our loop, times absolute value of the derivative of our magnetic flux with respect to time. So that's why we came up with this expression for the magnetic flux, because we're now going to take the derivative of it. Okay? By the way, in this particular loop, N just happens to be equal to 1. We're imagining just a single turn of wire, so N is equal to 1. And then what we're doing is we're taking the derivative with respect to time of B times L squared. Now, somebody tell me, we're taking a derivative, we want to pull out constants. What can I pull out as a constant, if anything?
L squared.
Yeah, L squared, but B is not constant, okay? B is decidedly something that's changing, so what we have is L squared as a constant, and then left over dB by dt. So it's B that's changing. This is one of those examples I told you about, right? It's either the area that's changing, it's either B that's changing, or some kind of angle that's changing. This is one of those examples where B is what's changing, okay? So, how can we deal with that? B as a function of time, I'll just write it back down, is 0.45 Tesla per second squared times t squared plus 0.9 Tesla per second times t plus 1 Tesla. Okay? So if this were constant, of course, then dB dt would just be 0, and I'd have no induced EMF. Faraday's law wouldn't really be coming into play. But because this is something that's changing in time, this is non-zero. So let's just evaluate the derivative of this B field strength with respect to time. Let's do it term by term. I basically have a t squared in the first term, right? What happens when I take the derivative of that? T squared becomes 2t. I'm just going to merge that factor of 2 with the 0.45, so it becomes 0.9, okay? So at 0.9, t over second squared, Tesla over second squared times t, which is time, okay? All right, now over here I have just some constant times t. What's the derivative of t? Just 1, so I just have that constant. 0.9 Tesla per second. And then for the last term I have a constant. What's the derivative of a constant? 0. All right, so check this out, everybody. At time, t equals 1 second. Okay, that's the first question we're asked is what is the current induced at time t equals 1 second? So guess what? We need to plug that time into here to see what happens. So what does it work out to? Yeah, it's 1.8. So at t equals 1 second, we have dB dt equaling, yeah, you can see it works out to 1.8. I'm not going to write that down. Right, so you have 0.9 times 1 plus 0.9, 1.8. Sorry, this is Tesla per second, if you look at the units, okay? Good up to this point? So then, what's the induced EMF in the coil at that time? That is, I'm going to take, again, L squared times the magnitude of dB dt. So now I have a number for that. I'm going to plug it in here. That's going to be 0.195 meters. That's the length converted to meters, 19.5 centimeters. Square that and then multiply by 1.800 Tesla per second. And this works out to something. What does it work out to?
.8 times 10 to the -2.
Yeah. So here, let's make sure we have enough digits. So 6.845, I think, are the next two digits. 10 to the -2. We actually round to 3 sig figs in this case. Now, here's what we say about this. It's an EMF. What unit do we expect? Volts. Yeah. This should be in volts. I'll leave it to you to show that meters squared times Tesla over seconds is volts. We're not going to do that today. It's volts, okay? And next, we can finally get the induced current. Because that EMF induced in the coil, of course, is the current that's induced times the resistance, right? It's just Ohm's law. So here's what we have. The induced current is the induced EMF divided by R. So that's 6.845, 10 to the -2 volts, divided by R, which is 0.15 ohms. So now this gives us the actual current. And what is the value of the actual current?
0.46 amps.
Yep, so it's 0.456 amps. And we already determined it's clockwise, okay? So in this situation, at this time, you're going to get 0.456 amps of current going clockwise. But if we choose a different time, like t equals 3 seconds, we'll get even more current because, see, the B field is changing faster and faster as time goes on. And we get more and more induced current as time goes on. So let's do, as a final step, at t equals 3 seconds. Here's what we have. We have dB dt. That's 0.9 times t plus 0.9. So that's 0.9 Tesla per second squared times the time is 3 seconds. And then add to that 0.9 Tesla per second. What does this work out to, everybody? So 0.9 times 3. What is it? 3? So it should be 3.6, right? Tesla per second. Okay? That means the induced EMF, we have the formula, so I don't have to work it out again. It's just, remember, L squared times the, oh, I'm sorry, guys. Can I back up a second? I made a small typo, basically. Right at this line here, where it said L squared times, this should just say dV/dt, okay? That should just be the derivative of the magnetic field with respect to time, right? Okay? So we have L squared, which is 0.195 meters squared, times the derivative of our magnetic field, which is this, 3.6 Tesla per second. Okay, and that works out to how many volts?
uh, 0.137.
Yeah, 0.1369 volts. And then that means our current, the current is that voltage divided by the resistance. Okay, so it's 0.1369 volts divided by the same resistance, 0.150 ohms. And now we have our current, which is 0.913 amps. Okay, so there is the induced current at 3 seconds, and again, we worked out at 1 second, it's this value. Okay? Any questions on this? All right, we're going to do lots more examples. Pretty much from here until the end of Wednesday is just more stuff like this. So we're gonna keep going, okay? I want you to try this out. Okay, take a minute to work on this one. So you have a circular loop of wire. It's and the diameter, by the way, of that loop is 27.5 centimeters. It's inside of a uniform magnetic field, and the uniform magnetic field is coming out of the page. Let's say that the strength of this magnetic field is decreasing at a constant rate. So it's a little bit less complicated than before. It's just decreasing at 0.1 Tesla per second. That's how quickly it's going down, okay? So let's say the loop has 15 turns of wire in it, and the total resistance is 1.5 ohms. How much current gets induced in the loop? And is it clockwise or counterclockwise? All right? So again, Lenz's law tells you the direction. Faraday's law will tell you how much current gets induced. So take a minute, take maybe 5 minutes. This one's a little bit longer to work this out, okay? So try to follow some of those steps from the last problem. See how to do this.
give you the right induced EMF.
It's a point. How about we start with the direction? Has anyone got that yet? Which way are we going?
I want to say chemical.
All right, let's put that one to a vote. Who's saying the current goes clockwise? Counterclockwise? All right, so I think we understand that part. Does anyone want to go through that again? No, okay. How about calculating the current? That's not quite as straightforward, right? So let's go through it. Anyone have an answer? I think I saw some of you got something. What's that?
5.94 times 10 to the negative 2.
Yeah, you got it. So 5.94 10 to the negative 2 amps is what you'll see here. So let's go through it step by step. We always start if we're going to apply Faraday's law. So actually, just on the side, I'm going to write what we determined for the current direction. This B field is decreasing over time, and what needs to happen is a clockwise current, let's say clockwise, counterclockwise current like this is going to be induced in the coil, right? Right, so now let's apply Faraday's law. Faraday's law says the EMF induced in this coil is the number of turns times the derivative of the magnetic flux going through the coil, like this, okay? So that means first thing we should do is write some kind of formula for the magnetic flux, plug that formula in there, and then see what its derivative ends up being, okay? That's kind of the process with Faraday's law, by the way, right? With whatever situation you have, write down some expression for the flux through your loop, and then you'll take a derivative of it. That's what's going to happen. Okay, so the flux through the loop, let's do that. This one, again, not so bad. We have another uniform B field and a flat surface. So just like before, even though the general expression is integral B dot dA, we can get around that as just B dot A, where A is the entire area of the loop, okay? So that means we have the B field strength times the total area of the loop times cosine of some angle, which this is just like before, right? If the loop is in the plane of the page, its area vector is perpendicular to the page, just like the B field, right? They're both coming out at us. So there's 0 degrees between them. Okay, we clear on that? So in other words, you're getting the most possible flux by orienting things this way, right? Okay, then let me ask you, what is the area of this particular loop? That's just pi r squared, or r is the radius, okay? So the flux is just the strength of the B field times pi r squared. Now in Faraday's law, again, to bring it back to that, we're taking the number of turns of wire in this loop, because basically each one of them feels the same EMF, so we have to add them all together or multiply by n. That's another way to think about it. And we'll take the derivative of this expression, because that's our magnetic flux. So that's the derivative with respect to time of B times pi r squared. And again, some things are constant, some things are changing. What's the thing that's changing here?
The big
B field strength is changing. Everything else comes out. Now, by the way, you can have multiple things changing at the same time, in which case you'll have to do the product rule here, but we'll see that in the next lecture. You'll have an n times pi r squared as constants out front times the magnitude of dV dt, because again, we already figured out directions through Lenz's law, Faraday's law, we're just considering the absolute values, okay? So, this is actually something we have a number for. The time rate of change of V is 0.1 Tesla per second. That's how quickly it's decreasing, okay? So that number we were given of 0.1 Tesla per second is our dV dt, okay? It's our time rate of change. So what's n? That's 15 turns of wire, so 15 with no units goes first. And then we have pi times r squared. Now, we were not given a radius, we were given a diameter. So I'll take half of that diameter, half of 0.275 meters, and I'll square it, like this. There's pi r squared. All right. Then we have dV dt. Again, it is decreasing, but we're just looking for the absolute value, so we plug in 0.1 Tesla per second. So this is our EMF. What would that be? Multiply that out.
Gymnastics. Getting 890.
0.0891.
0.08, and then 909 volts with 3/6. So what's going to happen is we have current, we have the same amount of current flowing through this loop as if we had a perfect battery with no internal resistance with this voltage, okay? It has the same effect as far as the current that flows as having a battery with that voltage, okay? Which means the current that flows is going to be given by Ohm's law. So we have, when we solve for the current, the EMF induced divided by the resistance in our coil. So that's going to be 0.08909 volts divided by 1.50 ohms, and giving us what? It's just what Sean said at the beginning.
5.94 times 10⁻².
Yep, so 0.0594, I'll write it decimal form, but yeah, it's 5.94, 10 to the minus 2 amps, and yeah, counterclockwise. Okay, so that's how we do these problems, right? Find the magnetic flux through whatever loop is relevant. We'll calculate a derivative, and then also multiply by n to get the induced EMF. And then it's just a simple application of Ohm's law to get the induced current. For the direction of that induced current, you use Lenz's law. Okay, so if you can kind of fit all those things together, you'll be in good shape. All right, any questions on this? We're going to do another example. So far, the examples that we've seen have involved changing the magnetic field strength of whatever magnetic field is going through our coil, okay? In this case, we're going to talk about changing the area. Now that may seem kind of weird at first, because if I have a coil like this, how am I going to change the area? Am I just going to pull this thing apart? That's pretty difficult, right? So that's not generally what we're talking about. Instead, we're talking about something that looks more like this, okay? So it seems like kind of a strange setup, but it actually leads us to something more general. We have two long parallel rails. So one up here, one down here. And these just extend really far out. So we can just move along those rails as much as we want. The rails and this connecting wire here that connects the two rails, they have negligible resistance, okay? But what we have is a metal bar with length L, which we put across the rails. And in doing so, we can create a complete circuit, right? We're also going to say that there's a resistance in this bar, which we'll call R, okay? So length L, resistance R is this metal bar that we place across the rails. Now assume that this bar is able to just sort of slide along the rails, left to right or right to left, whatever you want, without any friction, okay? Okay, so this whole apparatus is in a uniform B field. Let's just say it's going into the page. There's nothing special about that, but let's take that as our example. So it's in this uniform B field going into the page. Question is, what happens when we push the bar to the right at a constant speed, which we'll call V? So I hope it's clear what our loop is, right? We have a complete loop here where current could potentially flow under the right circumstances. What has to be happening for current to flow in that loop? A changing magnetic flux. Yeah, that's right. And is there a changing magnetic flux? Yeah, it looks like it, because we're not changing how strong the B field is, but what we're effectively changing is the area of our loop. The area gets bigger if we push the rail this way, if we push the bar to the right, and it gets smaller if we push the bar to the left. So either way, we are effectively changing the area, and yeah, Faraday's law is going to come into play. We're going to induce some current to start flowing in this case, okay? Now actually, let's first establish, in this particular setup, what direction is that current going to flow? Clockwise or counterclockwise from our point of view? All right, we'll do another vote, all right? Who says, okay, I explained the situation, right? Who says we get a clockwise current resulting from that? Who says we get a counterclockwise current? Yes, it's counterclockwise. All right, let's just go through the steps real quick, right? Okay, if I'm pushing this bar to the right, is my flux going up or going down? Flux is increasing or decreasing? Our flux is increasing, right? Because we have more and more field lines going through this loop as we increase its area, right? So we're increasing flux. What does that mean about our induced B field? It's got to be opposite this guy, right? In other words, we induce a B field that's coming out of the page. And the way for that to happen is to have a counterclockwise current flow through the loop. Okay? So in this particular case, it's counterclockwise. You can guess that if we push the bar the other way, clockwise, right? All right, so let's work out what that current is. Okay? That's what we're going to do next. So we'll do that part on paper. Here's the picture I want you to have in mind. We've got these two rails, one up here, one down here. They're connected by some sort of wire. All this is negligible friction. But again, we have this bar which goes across and gives us a complete circuit. And this has some resistance that we can't just ignore. We're calling the length of the bar going this way L. And we have this B field that this whole thing is immersed in, which is going into the page like that, okay? So I'm going to draw a few other things on this diagram which will be useful going forward. I'm going to call this distance right here between the very left end and the bar, I'm going to call that X. Okay? And whatever speed we're pushing this thing forward with, or velocity, I'll call that V. Okay, so that's what's going on. And as we said, this is our induced current going counterclockwise. All right, so let's now apply Faraday's law to this to figure out what our induced EMF is and what our induced current is. Okay, so here's Faraday's law. Remember, the basic statement is the induced EMF, epsilon, is equal to the number of turns in our loop times the derivative of our flux through the loop. And again, we're doing absolute values here. Now, how many turns should we put in? What should we say n is equal to?
1.
Yeah, in this case, you just have a single turn, okay? You just have one single loop around. We're not doubling over or anything like that. What about our magnetic flux? How should we think about that? Well, again, this is one of those nice examples where we do not need to do some kind of integral because we have a perfectly uniform field and a flat surface that the field lines are going through. So I can skip right ahead to, this is just B dot A, which is our B field strength times whatever this area is, times cosine of some angle, which again, we have a nice orientation, which maximizes the amount of flux, right? 0 degrees, okay? Between our B field and our area vector, okay? So, let me ask you this. B, that's just some uniform thing. That's not changing, that's just some number. If we had it, we could plug it in. But the area, that's what's changing in this case. And what, based on what's on the page already, what is the formula for that area?
L times X.
Your area is L times X, that is correct. So basically we have BLX, okay? For our flux, that's the magnetic flux going through this loop. The induced EMF in that loop, therefore, is n equals 1. And then we have the derivative with respect to time of BLX. Of those three variables, which ones are changing? It's X that's changing. L, of course, is just the length of your bar. That's not changing. B field, we're assuming, is uniform and also not changing over time. So it's X, right? Because X increases as we push it further to the right, correct? So what we have is B times L times dx dt. What is dx dt? What is that? Yeah, it's the velocity, and then we take the absolute value of it. That's called our speed, right? So, yeah, right there is just saying, you know, how far do we move dx in how much time dt? That's speed, okay? So this is the speed which we get by v. So that means my induced EMF is actually just B times L times B, okay? And then if we apply Ohm's law, that says that very same induced EMF is equal to I times R, right? It's just the current that results times the resistance. And we're just imagining, for the time being, all the resistances in the bar. Kind of makes this a little simpler. So what we have is BLV for the EMF equals IR. So the induced current is, you know, just BLV divided by R. So those are the two results I wanted to show you, here and here. Okay? Make sense? Do we have any questions on how we got there? So basically that's how it's going to work when it comes to a changing area, at least with this geometry. There's different ways you can do it. And if there are no questions, let's do the summary. EMF induced BLV. Current induced is just that divided by R. That's it. So there's a couple other things we need to get to. We've got 10 minutes, so not going anywhere. First thing is, I want to address where is this energy coming from, okay? When we cause current to start flowing in these various scenarios that we've seen so far, okay? Of course, that requires an input of energy, right? And that energy is just not coming for free. This is not some kind of magical process where that electrical energy is coming out of nowhere, right? We have to pay some kind of price for this. We have to put that energy in at some point. But it might not be obvious where that's happening, right? I mean, for example, in this scenario, when current starts flowing, we have electrical energy being produced. Where is that coming from?
The kinetic of the bar moving.
Okay, and where is that coming from?
Whoever's moving the bar.
It takes work, mechanical work to move the bar. You can't push the bar without inputting some work. And guess what? The more electrical energy you generate, the more work you're gonna have to put in. You're gonna have to, it's a one-to-one thing, okay? Assuming perfect conditions with no friction. In reality, in less than perfect conditions, you get a little bit less out than what you put in because you lose things due to friction and whatnot, right? By the way, this is not how we're gonna realistically generate electricity, but it illustrates the point, right? So, okay, first thing. We kind of have some idea that mechanical work, like involved in pushing the bar, has to do with this. So let's start with a free body diagram of the bar itself, which shows the forces that act on it, right? Now normally, if you have to kind of like push something to keep it moving, it's because there's friction, right? Like I have to provide a steady force to move this along the table because friction opposes my push. But here there's no friction, okay? So what forces are acting on the bar? No friction. All right, let's assume, let's forget about gravity. Let's just say, you know, we're looking from the top down, so gravity's going into the page, and there's some normal force holding the bar up, going out. I'm just talking about sideways forces, like left to right.
Force on the push.
There's some force you're pushing with, let's call it F push. That has to be there. Kind of looks like something might be opposing your push, right? Because if all that's happening is I'm just pushing and there's nothing opposing it, I'm not going to move at a constant speed, I'm going to accelerate the bar. So there's something opposing my push, but it's not friction.
Would it be the magnetic field?
The magnetic force, okay? Exactly. You have current running through the bar, and that is in the presence of a magnetic field. So there's going to be a force on that. And guess what? It's always going to work out to oppose the push, okay? So whatever force or even torque that you have to put in to start generating this current, there's going to be an opposing force or torque against that, okay? And do you guys remember how this magnetic force works? I'm just going to claim that it's, you know, going to the left, but for this situation, we use IL cross B, right? So that means we take our right hand, just to get the direction, fingers in the direction of the current. We're just thinking about the bar, so that's straight up. And then we curl in the direction of B, which is into the page. Then our resulting force is this way. So as you push, you're going to be pushing one way with an opposing magnetic force. And guess what? The magnetic force gets stronger as the current gets stronger. So the harder your push, the more current you generate, but then the more the opposing force grows as well, okay? So it's always this push and pull. So if the bar moves at a constant speed, let's say that's the case for simplicity, let's apply F equals ma to it. Basically, we have a push and a magnetic force going in two opposite directions. So when we sum them over, we just have F push minus FB. And then we're saying there's no acceleration. We move at a constant speed. So we get 0 on this side, okay? So what does that mean? It means whatever we're pushing with, it's exactly as strong as our magnetic force. Which I'm going to remind you, our magnetic force is given by IL cross B, and we're just finding the magnitude of that right here. So what's the magnitude? It's the current, which is I, times L, which is the length of our bar, times B. And the current and the B field make a 90-degree angle with respect to one another. I hope you guys can see that, because the B field is going this way, the current's going up, so they're at 90 degrees. And so to simplify, actually before we do that, let's take the result we just worked out. In this scenario, what is the current? It's BLV divided by R. So let's put that in for the current right over there. That's what we're going to do. Just plug it in. So we have BLV divided by R. That's going in for the current times L times B. Sine of 90 just gives you 1, so we'll leave it off. So to put this in a more, I don't know, compact way, we have 2 factors of B on top, so we have B squared. We have 2 factors of L, so we have L squared. We have 1 factor of V, and then on the bottom we have 1 factor of R. So that's what we have, B squared times L squared times V divided by R. That's the force you have to push with to get this to work. Okay, to get the bar to move at some constant speed. Okay? So, if we know what that force is, we can then ask the following question. What is your power output as a person pushing this bar? Like, how many watts of power are you outputting? How many joules per second are you putting into the bar? Okay? Well, I don't know if you guys remember this, but mechanical power is work per unit time. We'll write it as dW dt. It's how much work per unit time I'm putting in. Okay, it's the rate at which I'm doing that. And I don't know if you remember this as well, but work is just force acting over a distance. Okay? So on top, for work, I'll put that as the force of my push times dx, some tiny infinitesimal distance over which I exert the force. And then that's divided by t, and notice we have dx dt right there. You guys recognize that? That's v, that's how fast the bar is moving. So it's basically my power output in moving the bar is F push times v, which is the speed of the bar. Which means, if this is the force of my push, we just worked it out, pop it in right there, B squared L squared V divided by R times another V to get the power output. So basically that V is squared when it's all said and done. Might put it together in a more simple way like this. BLV all squared divided by R. Okay? Okay, so check this out. That's my power output, mechanical power output in moving the bar. What's the electrical power we get as a result? You guys know a way to calculate that? Electrical power?
I squared.
It's I squared R.
R squared,
Yeah?
sorry.
Yeah, so if we know the current, right, and the resistance, we can calculate the electrical power as well. You can think of this mechanical power as like input and this electrical power as like output, right? So the current, we know what that is. It's BLV divided by R. We're squaring that whole thing in our familiar formula, right? But then we multiply by R. So what does that work out to when it's all said and done? Well, we're going to have BL and V all being squared on the top. And then we'll have 1 factor of R on the bottom if you collect all the terms. So what do we have? We have BLV all squared divided by R. These match, don't they? What does it say? Okay, the energy you put in performing mechanical work equals the energy you get out in terms of the electricity generated in perfect conditions which don't exist in the real world, like friction not being present, right? So perfect circumstances, you put in exactly what you get out, okay? Under less than perfect circumstances, you get out a little bit less than what you put in because you waste some energy in generating heat via friction and things like this, okay? But energy is conserved. It's really important to remember that this is not some kind of magical form of energy that's coming out of nowhere. It's coming from the work you put in to put the motion in place in the first place, okay? So we'll talk about this stuff more on Wednesday. And again, there's a quiz on Wednesday, so I'll see you then.